Hello, and welcome to this video on absolute dating, which is also called radiometric dating. This way of telling time is called absolute dating because it enables us to put actual numerical ages onto rocks, and it's referred to as radiometric dating because it utilizes the processes of radioactivity to do so. So you will find this methodology referred to under the terms of both absolute dating and radiometric dating. Now, to begin with, we need to start thinking about atoms. And the first part of that is atomic number. So hopefully you've had some chemistry in your past and you can remember that atomic number refers to the number of protons in the nucleus of an atom of a specific element, because this is in fact what defines the elements. Hydrogen has 1 proton in its nucleus, helium has 2 protons in its nucleus, and every different element will have its own unique number of protons in that nucleus. Now, next question, what is atomic mass? Well, because the electrons weigh practically nothing, they have practically no mass, they have no mass, we instead, the entire atomic mass is made up from the masses of the protons and the neutrons in the nucleus. So atomic mass actually is most often used to refer to the number of protons and neutrons in the nucleus. You combine that number, you get atomic mass. Well, this brings us to the hopefully we're back now. So isotopes of an element, here is hydrogen. We'll see if we can do it this time. Hydrogen can have either 0 neutrons, 1 neutron, or 2 neutrons in the nucleus. So each of these different flavors of hydrogen is a different isotope of hydrogen. Now, the important thing here is that there are multiple different configurations of neutrons in these atomic nuclei, even though there's really only one configuration for those protons for each individual element. This means that it's possible to have conditions that are unstable inside of this nucleus. So you have all those protons in there. They are positively charged, and because of that, they repel one another, like charges repel. And so all of these positively charged protons inside of that nucleus will repel each other. And that makes the nucleus rather unstable. It takes just the right configuration of neutrons to sort of spread out those protons and minimize that repulsive force. Okay, so again, protons and neutrons, all of those protons are attempting to get away from one another, and you need just the right number of neutrons to create stability. Now, sometimes that nucleus is not stable, and when a nucleus is unstable, it can spontaneously change to a more stable form. The process through which this happens is referred to as radioactive decay. Now, with radioactive decay, you always start with a parent nucleus. Okay, so this is just whatever you have to start with. This is the unstable one, and then you can't say exactly when, but at some random time, it will decay into what we call the daughter nucleus. Why parents and daughters and not dads and sons? I have no idea, but this is the nomenclature that is used. So in order to go from a parent to a daughter, you have to emit or absorb some subatomic particles there. So you're actually physically going to be changing the number of protons and or neutrons inside of that nucleus. So just to restate, what is the process of radioactive decay? What is radioactive decay? It is a process that occurs when an unstable isotope changes into a new, more stable form as a result of an emission or a capture of subatomic particles. We're talking about protons, neutrons, and electrons. There's various things that can happen that can change the configuration of protons and neutrons inside of that nucleus. For example, here is a radioactive element, and you could emit a particle as well as some energy. Maybe you're emitting an electron, maybe you're emitting a photon, just to make all of the energy sort of balance out and work here. But no matter what's happening, you are doing something that is changing the number of protons and or the number of neutrons inside of the nucleus. Now, obviously, if you do change the number of protons, you're going to have a brand new element. And in geology, most of the decays that we will be referring to are going to, at least at their start and end point, refer to different elements. So you do have a parent element and a daughter element that are different versus the case where you decay into a different isotope of the same element. Okay, so that kind of begs the question, when does radioactive decay begin? Well, it begins as soon as a mineral is formed. A mineral, especially the kind of mineral that's used for this type of dating, acts as a little time capsule, and it holds on to all the elements within it. So that's going to include all of the parent and all of the daughter. And as long as those are all contained within the mineral, it will be useful for absolute dating. So as soon as that mineral is first formed, decay into the daughter element begins immediately. Now, what does immediately mean? Well, the process of decay is in some ways random, but we can describe the randomness of the system by talking about its half-life. So if you have a sample, it might have millions of atoms, okay? And there's no way to point to a single atom and say, oh, that one's going to decay. They don't all decay at once. They do it based on a really specific rate that we can measure. We can measure how rapidly these things decay. What we know is that our time clock, we'll talk more about how the time clock works in a second, but our time clock starts the moment that the mineral is formed. All right, half-lives. Half-lives are super important in this process because they help us to understand, they enable us to calculate how long it has been since that mineral formed. The formal definition of a half-life is the time it takes for half of the parent isotope to decay into daughter atoms. Note that this doesn't depend on how many atoms you have. It's kind of like if I were to flip a coin, I'd have a 50% chance of heads and a 50% chance of tails. It doesn't matter if I have 1 coin or 100 coins, each coin still has a 50-50 chance of flipping heads or flipping tails. However, if I was to flip all 100 coins at once, I would expect about 50% to be land heads and about 50% to land tails. I couldn't tell you which would do what, but I could still say something to describe the system. That is exactly what this radioactive decay process is like. We can't point to individual atoms and say what they're going to do, but we do know the rate of change of the system. So how we determine this scientifically? Well, we first have to measure what that decay rate is, what the half-life is, and then we need to look at a sample and compare the amount of parent isotope to the amount of daughter isotope. There's a whole other video from a different lab that actually does this work to explain in more detail how those ages are calculated, so be sure to check that out. Okay, here we have a graph, and this graph is going to be so important, okay? This is a decay curve, or at least we're going to write the decay curve on here. On the left axis, it says proportion of element present. We're actually going to make that the proportion of parent present. And on the bottom is number of half-lives. That's time, right? So if your half-life is 20 years, one half-life would be 20 years. If your half-life is 500 million years, one half-life would be 500 million years, right? So number of half-lives is just a way of sort of simplifying our time axis. Now, down here, we're going to start at time 0. And at that time, how much parent do we have? Well, it's all parent. So at time t equals 0, we have 100% parent. Great. Now, at time 1 half-life, that's just supposed to be 1. Well, half-life is the time it takes for 50% of the material to decay. So at 1 half-life, we have 50% parent. The other 50% would be daughter, okay? At 2 half-lives, we are going to have half of what we had before. At 3 half-lives, half of that. At 4, half of that. And we're basically forming, let's see if I can do this, a little hard on the screen. But you're forming this decay curve. It's an exponential decay. At the same time, you could also think about what's happening to the daughter. The daughter isotope starts out with 0, and as time goes on, you get more and more daughter. So this line represents the percentage of the sample that is daughter elements, and over here, this line represents the percentage that is parent. Here is sort of a not hand-drawn graph, just to show you that. And if you want to figure out the age of a sample, all you have to do is take the number of half-lives elapsed times the duration of the half-life, and you get an age. So for example, if a half-life is 100 million years and 2 half-lives have gone by, then your sample is 200 million years old. Okay? So that's all I've got about half-lives and radioactive decay. Please check out the other videos for additional background and have fun with it. The math can seem a little bit tricky at first, but it's not really the math that's hard. It's wrapping your mind around the processes underlying the math. So just keep that in mind if you run into any trouble.